Welcome back for round 2 of Kafka Summit 2020. Very glad you're back today. Just a few housekeeping items before we launch into our morning keynote. Remember, I know I keep saying this, but remember to rate your sessions that you attend as they conclude on the app. That's very, very important for us to get a sense of how things are going for you, great feedback for speakers, and all of that. So do that. That's very helpful. Make sure you're tweeting the show with the Kafka Summit hashtag. I've loved seeing the selfies that you've been posting. Please give me more of those with the streaming selfie hashtag. Just you, wherever you are, probably in your home office, but wherever you happen to be enjoying this content. And again, if you can get a pet in there, some of your family, let's have some fun with that. Also, make sure you fill out the event survey after this is done. This, again, people are pretty new at making all virtual conferences, including us, and we want your feedback. We want to be able to shape future events. We're hoping to meet in person in the spring and in the summer of next year for London and for the North America Kafka Summit, but we still want your feedback on how this went so we can continue to improve. Next up, we have Jay Kreps. Jay is, as you may know, the co-founder and CEO of Confluent. Prior to founding Confluent, he was the lead architect for data infrastructure at LinkedIn. He's among the original authors of several open source projects, including Project Voldemort, which was a key value store, Apache Samza, which is a stream processing system, and of course, you may have heard of it, Apache Kafka. Today, Jay is going to talk about the rise of two big trends. These are what economists might call secular trends, or things that change meaningfully over long periods of time. This kind of trend is a thing that is just happening, whether we want it to or not, so we would do well to recognize it and respond to it. Specifically, Jay is going to talk to us about event streaming and cloud-native systems, and what he thinks our response ought to be. Jay, take it away.
Hi, everyone. I'm Jay Kreps. I'm the CEO of Confluent and one of the co-creators of Apache Kafka. I want to welcome you to day 2 of Kafka Summit. I'm going to be talking today about two trends that I think are really happening in the world right now. One is the emergence of Apache Kafka and event streams as a fundamental part of the modern computing stack. And the other is the rise of public cloud and especially cloud-native data systems as the way forward with data. And I'm going to talk about how these two trends intersect and a big problem that I think comes out of that and what I think the solution is. So let me start with event streams and Apache Kafka. This is something that is near and dear to all of our hearts and that we know a lot about. But nonetheless, I'm going to give my take on what's happening in this area. I think whenever something new happens, there's kind of a reductive view of that thing and an expansive view. And the reductive view is, well, nothing much has changed. And the expansive view is, what if this was true in the large? What would be new and different? And the reductive view for Kafka is, it's just another message queue. It's just another data pipeline. We've had queues in the past. Now this is a more scalable queue. It can solve bigger problems, but there's nothing really fundamentally different. And obviously, I think that's wrong. I take a much more expansive view of the space, and I'll try to explain what I think is happening. And I think that this is a fundamental change in what we think of in the world of data management, data infrastructure. I think classical databases came out of a paradigm that was really built around storing data, that ultimately you have this pile of data, and periodically you want to look up little bits of it, you want to poke or modify parts of it, and this is meant to be what you need to serve an application. After all, the data infrastructure is meant to be the infrastructure that supports your application. So it's worth asking if this is really all we need. After all, databases have been enormously successful. This type of application has been enormously successful. But I think there's something that is really fundamental that's missing in this view of the world. And that's that our conception of an application has changed. The world that databases were created for had applications which, one, were islands of data in and of to themselves. You would input data through some UI. You might fetch it back in different reports or views. But ultimately, this application was largely independent. And secondly, the application was really built for humans. Ultimately, the goal is store the data in this big pile and look up the pieces of it that you need when a human opens the app or goes to the website or refreshes the screen. That's when the action happens. Ultimately, the data system is passive. the human is active and is causing the data system to do work. And I think both of these assumptions aren't really true in the world now. Now I think our applications are no longer islands into themselves, and they're no longer passive. They need to interact with all the parts of a big, complicated organization. And when you take that more limited data capability and you try and apply it in the large across the whole company, I think what you get is a giant mess. And we're all familiar with this. This could be the architecture of the internals of any company, but probably it would be 1,000 times more complex. And where a lot of the complexity has gone is into all these squiggly lines, into all the integrations and interchanges, how this application, when it changes, impacts this other application. When this calls this, then this other thing should happen. And the reason this is happening is because applications don't stand alone anymore. Our business is built out of all these pieces of software that come together into one digital exoskeleton, one system that runs the operations of the company. And modern consumers expect all these to work together. They expect that when a customer experience is delivered over here, all the other parts of the apparatus adjust and take that into account. And the internal operations of a business demand this as well. If a sale occurs in this part of the business, that should percolate out into all the actions that need to be taken downstream to fulfill the logistics, report on this, take action on whatever's next. And to do that requires a very high level of integration. And this has been forced on us, but without really having the right technology to back it. And the key thing that has changed, in my view, is that in this modern world, applications don't stand alone, and the user of an application is no longer entirely or even primarily just a person. In large part, the user of our software is often more software. It's often a piece of software that needs to integrate, that needs to key off some change, that needs to react and respond. And because our software estates are now integrated across many, many different applications and systems, this is a critical part of what a modern application has to do. And this is what I think more than anything has driven the emergence of Kafka and event streams and stream processing. This is meant to model a world where data management isn't just about storage. It's about both storage and the flow of data. It's about things happening and reacting to them. And it's built in a way that's meant to serve not just a human user with a UI, but actually a computer user, right? Software systems, after all, work all the time. They're always operating, they're always processing, they're always calculating. It doesn't really make sense to do things just when the application is open or just at the end of the day when some batch job runs, if that's being done by software. The software doesn't go to sleep at night, after all. It can work all the time. And this, I think, is the fundamental change that has driven the rise of this area. And I think it's much bigger than just another message queue. I think it's actually a fundamental change in what we think of as the capabilities that any data platform ought to have. And I think in the large, this has a huge implication for the architecture of companies. I think the world of all those squiggly lines kind of interconnected in ad hoc ways, I think that's coming to a close. And I think we're seeing the emergence of an event streaming platform, something that can connect many parts of a company across many systems in a decoupled way and can allow this company to actually act as one. And this is a place where you can go and see the stream of all the activity happening in the company across different parts, tap into that, react. I think this is a very powerful thing. So that was the first trend. That was the rise of Kafka and event streams. That brings me to the second trend, the rise of the public cloud and especially of cloud-native data systems. And I'll explain what I mean by that. But first, I want to talk just a little bit about this area. Like with Kafka, I think there's a reductive view of the cloud and there's an expansive view. And the reductive view we've probably seen. So as this stuff came around, I saw a lot of things that said, well, there is no cloud. We're just renting computers. This is just somebody else's computer. And there's obviously a nice cynical take there. But I think we're far along enough now to see that the change that the public cloud has brought is actually incredibly cross-cutting. It touches every aspect of how applications are built, how they're deployed, how they're architected, how they're configured, how we observe and operate them. Everything has changed. And the CNCF has tried to popularize this phrase cloud native to describe this. And they've mostly talked about this in terms of application development. And it doesn't really have a precise definition, but I think it's actually a useful phrase. It's one of these things that we need to have a word for. I think it's been incredibly powerful. However, I think there's something that's missed in this discussion. Our discussion is mostly on application development. It's on how we write code. And that's something, of course, software engineers love to talk about because it's what they spend their time doing. But in a business, there is something more important than code. There's something that I think is more powerful, that is more durable, that provides even more capabilities, and that's data. I think ultimately businesses run on data, and the capabilities that we have around data come from the kinds of data systems and the primitives and abstractions they provide. I think that this idea of cloud native computing is at least as important when we think about what that means for data systems as it is when we think about what it means for application development. And my view on this came about early on. So it came about from my time at LinkedIn. Many people know that Kafka was created at LinkedIn, but it was actually one of a number of pieces of software that we ran there. LinkedIn wanted to be like Google in this respect. In those days, that was seen as a really important thing to develop these capabilities around data systems that could scale and to bring them to bear to help power the business. And so we went through this curve of trying to build out different systems, adopt open source technologies. And the first phase was always putting it to use for one application, making one application successful. But once we'd done that, that's when the hard part would come. That's when we would try to scale it out to work across the organization, to try and provide it as a fundamental primitive that anybody could have on demand for anything they were building whenever they wanted. And that was brutally difficult to do. And it was difficult not just for Kafka or for the key value stores or for Hadoop, it was difficult for all of them. Even the commercial software that we bought had that same scaling difficulty as we tried to offer it out. And as we went through this learning process of trying to figure out how to do it, we realized that fundamentally what we were trying to provide was a type of service. Now, it was a very primitive service. It was invoked often by customers coming and requesting something and filing a Jira ticket, but it was a service nonetheless. And often I would encourage the teams that were part of this overall effort to think in terms of the APIs they would have and think in terms of their internal customers being real customers that would have expectations, that we would have deliverables, that we would have SLAs, that we would try to support and make successful. And we realized that process of bringing something out to an organization was absolutely the hardest part. And we even joked internally that the privilege of getting to write custom data systems was really just a way to entice software engineers to do the hard work of actually operationalizing and scaling and operating them across a big organization. And because of this background, I was immediately impressed when I saw the rise of these cloud-native data systems. And for those who don't remember, the first releases in AWS actually weren't EC2. It wasn't really what we would think of as infrastructure as a service. It wasn't networks and servers. It was actually SQS and S3. It was cloud-native data systems. I think those two systems do a great job of actually drawing a line in the sand and saying, this is the service, this is what you get, this is what you pay per operation, and all the rest is magic that we handle for you under the covers. And those were just the first of what's been a whole wave of systems in this area. This idea of cloud native data systems and what they provide, it gets less attention, but I think it's equally important. And it's equally hard to define. I don't think there's a single characteristic you could point to where you would say, oh, it means this. It means that they're elastic. It means this other thing. But I think there are a set of things you would insist on. To say that something is a proper cloud-native data system, it has to be able to elastically scale. It has to provide capabilities to you in units that are serverless, that scale just with your needs, that you don't have to think about arbitrary servers and their type and configuration to figure out what you're getting. It has to be able to grow without bound. It has to have API-driven operations. It has to be global and work across different environments, across regions and availability zones. These are a few of the things I think we would insist on for any definition of a cloud-native data system. And the key point is none of these characteristics are shallow. None of them are things you can just take an existing piece of software and bolt on top and say, okay, we had this do-it-yourself software system, now it's a cloud-native service because we've bolted this on top. You actually can't. These are deep, cross-cutting concerns that are about how the system is architected, how it's operated, how it's developed, how it's throttled and managed. These are hard things that are right at the core of the design of these systems. I think this is a really important observation because I think that this type of system is the future. I think this is how we are going to be getting all of our data capabilities as we go forward. I think that the power of having this taken care of for you as a service is really liberating for teams that want to build things. I think it gets our best people into building the applications. And I think going forward, systems that have these characteristics are going to be successful. And the ones that don't are going to go the way of the dinosaur. And that leads me to what I think is a big problem. So if cloud native data systems are the future, and if Kafka and event streams are becoming a foundational primitive in how we think and work and build modern software systems, well, we have a real gap because most people's experience of Kafka is far from cloud native. You may start with the idea of relatively simple primitives, event streams, events, consumer groups. Like these things make sense. They have no aspect of server or low-level detail tied to them. But when you go to get it, there's actually quite a lot there. You kind of lift the hood and suddenly to get those things, you're dealing with deployment scripts and security patches and upgrades. You're fiddling with Zookeeper. You're learning more than you probably wanted to about garbage collection in the JVM. There's a lot of real toil to actually getting Kafka and actually delivering it, and much more so if you want to do that at scale. And I think that this is a big issue. In fact, we might ask, if these cloud native capabilities are so important, why is Kafka winning at all? And indeed, this is a question I asked myself when Kinesis was first released. So I was working at LinkedIn. The team there had spent a lot of time building Kafka. We'd released it as open source. So it was a little bittersweet to see AWS release a service that had very similar APIs right down to the kind of wonky consumer API that we had at the time, and even started with the letter K. And we thought, well, the good news is we built something that was worth copying. And the bad news is there probably won't be any Kafka in the cloud. And the reality, of course, turned out quite different. So over the years that followed, what we saw was not only did Kafka continue to succeed in the cloud, it actually flourished. And even before the rise of any kind of managed Kafka services, there was more Apache Kafka in the cloud than there was Kinesis. And so it's worth asking, well, why might that be? What led to that? And it turns out, although these cloud native capabilities are incredibly important, there's some things Kafka does really well. There's some things that really matter that Kafka gets right. And when I talk to people about this, and I ask them, well, why are you using Kafka? Why not just use Kinesis? I often get an answer that is something like, well, it's just a better product. But what does that mean? Well, I think it means a number of different things. One thing that I think it means has to do with the completeness of the offering. I think Kafka was built by a group of people that were trying to think through this problem end to end. What do you need to build an event streaming application? Well, clearly you need to be able to publish and subscribe to event streams. You need to be able to read and write. And you need to be able to do that in all the different programming languages. But it's not just that. You need to be able to store this event streams over a long period of time, whether they're compacted or retained by time. You need to be able to process them. The stream processing capabilities make it much, much easier to build rich applications around event streams. And you need the ability to connect into existing systems and capture streams of events without having to write ad hoc code. And I think it's not just a matter of solving all these problems, but trying to solve them together. Trying to have a set of shared abstractions, terminology, configuration, security practices that cover all of this. It just makes it much, much easier to build an end-to-end event stream application. And I think this completeness matters quite a lot. And I think it's definitely one of the things that's made Kafka successful. Another thing people point to is just performance. If you're trying to do something across a company at scale, one of the things that matters quite a lot is performance. How fast, how predictable, how low is the latency? Can you count on that? Can you count under that under odd circumstances? This is something I think Kafka does really well. And we just did a really thorough, fair benchmark, I think, of Kafka and some of the other messaging systems out there. We put it up on our blog. I won't try and recreate all the details here of that set of experiments. But the result of that was Kafka remains in the lead here. It remains the fastest system around the basics of messaging. And it's gotten better and better at this over the years. But I think that's not even the main thing. I think if I was going to point at something, I would point at something a little more abstract, which is I think that Kafka really comes with a point of view. It has an opinion on what's needed to build this kind of real-time event streaming application. And the people who have helped build it have a shared view of where it's trying to get to. And I think that this is something that's really hard to copy. I think if you try and build something that is, Kafka but as a service, or Kafka but with a few more features, it's really hard to actually overtake it because Kafka's continued to evolve over the years. It didn't start with that complete set of APIs. It started with just simple pub sub, and it evolved to that. It's really hard to surpass something if you're kind of just trying to catch up to it. It's sort of the copy of a copy phenomenon. Somehow the second copy just never has quite the same fidelity that the original does. Something's lost in translation. And I think that this gets at what people are talking about when they say Kafka is just a better product. It really comes down to 1,000 little things, little details that are needed to get an application right. And I think that this comes from something that is maybe an even bigger advantage. And maybe this is the number one advantage that Kafka has had. And that's the community. That's all of you. That's all of the people who have come together to make this happen. We tend to think in terms of software, in terms of features, in terms of capabilities, but the actual value comes when we build systems, when we build applications, and the knowledge for how to do that, how to do it well, the understanding and wisdom and practices that are built up by a group of people, this is actually incredibly valuable. And it's something that has given the Kafka community this point of view. It's something that has helped us to understand the applications that are important, the next feature that needs to be built. And it's also something that has produced another output, which is equally important. And that is the vast ecosystem of technology that integrates with Kafka. This is the data systems that have connectors, the stream processing systems that have integrations, the SaaS layers that integrate, all the legacy systems that can plug into and pull event streams out of. All of this is code that you end up not having to write. And I think that is incredibly important and easily overlooked. Kafka is a medium-large code base. It definitely solves some hard problems. It would certainly be hard to rewrite it. But the ecosystem of integrations is 1,000 times larger. It is literally 1,000 times larger. And rewriting that is impossible. And the set of things that unlocks in a company, the ability to actually plug into what you've got, that is one of the most important things in this space. And I think that touches at why open platforms tend to win. When I think about that competition with Kinesis, I think one of the most important things is that open platforms, they just have this weird tendency to survive and to thrive. And we've seen this over and over again in our industry, whether it's x86 or TCP/IP or Linux or email, they're all open in different ways. But that ability to have a community, to have an ecosystem of other technologies around it, that ends up being incredibly important and a key characteristic of their success. So all of those, I think, are reasons that Kafka, deserves to live. It deserves to continue to thrive. But I think if we want that to remain the case, while we move more and more of our workloads and environments to the cloud, while we rely and expect more and more on the capabilities of cloud-native data systems, it may not be possible to have these two things, these two trends, remain independent. I don't know if we can continue to have Kafka be this kind of self-managed or at best semi-managed, where some vendor kind of puts it on servers, but ultimately you're responsible for poking it and saying how many servers you want and what their characteristics are. I don't know if we can have this world where Kafka's a semi-managed thing, but cloud-native data systems are taking over the world. I think it's very likely that these have to come together. So those are a few of the reasons that I think Kafka has succeeded so far. But I think we have to ask the question, is this a permanent state of affairs? If Kafka remains something which is self-managed or at best semi-managed, where you can have a vendor that can put it onto servers as a service, but you're ultimately responsible for picking those servers and upgrading it and maintaining it from then on. Can that actually exist in a world where cloud native data systems are taking over in every other area of data management? And I think the answer is that it can't, that this isn't a sustainable resting place. And to try and address this, Confluent undertook what we call Project Metamorphosis. And this is both a Kafka pun as well as a reference to the transformation that we're trying to go through. We don't think you should have to pick between what makes Kafka great, the ecosystem, the point of view, all of that, and these cloud native characteristics. We think that you really ought to be able to get both of those together. And this isn't a small undertaking. It's not a matter of, like I said, just putting the software onto some servers. It really is deep development of a set of core capabilities. And so, these are things that in many cases we've been working on for years, but we structured a set of releases over the second half of this year to try and achieve this. And we've been doing these one per month, with each release focused on one of the major capabilities of cloud native systems. And so in May, we did the first of these, and it focused on what I think is, if anything, the most foundational characteristic, which is elasticity. This means that you can dynamically create Kafka clusters, you can scale them up on the fly. All the placement of data, rebalancing, expansion, that's all taken care of for you. And you can get rid of them, throw them away when you're done. And that elasticity, I think, is a core capability. And this video actually shows something I think is really cool. It shows an application going, from relatively light load, maybe 100 megabytes per second, and then suddenly scaling up to gigabytes per second of throughput. And this is something that when I saw it, I actually had mixed emotions when I thought about all the pain and suffering and late nights and emergency patches and outages and production mysteries that we went through at LinkedIn to try and achieve this kind of scale, this kind of trillion messages per day scale. And then I thought of the fact that you could just get this suddenly in a few clicks. I think it's both amazing, but also kind of cheapens it a little bit to be able to make it so easy. But I think that's exactly the point of what we're trying to do. We want the hard parts to be going and building your software, the thing that differentiates your company. And so these are the elasticity characteristics. This comes coupled with a proper usage-based billing model. And it seems almost kind of low level or crassly commercial to talk about the billing system, or at least very boring. But actually in the cloud, the billing model, the economic model by which you get the capabilities, that is the core of what it's all about. And so if you have an economic model, which is like, hey, pick out the instance type, I want a, extra large such and such instance, and I want this many of them, then you're not really providing a cloud native data system. And so, really making it possible to elastically create Kafka clusters, to get KSQL or connectors to scale those out as you need to, and to be able to have that all charge under the same account. This is a critical part of what we're trying to accomplish. The second month, we focused on cost effectiveness. Again, this may seem like a mundane thing, but I think this is one of the huge powers of the cloud. This is not just about making things cheap at scale. Actually, the first thing we did was focus on the low end, scaling costs down. Kafka has a reputation for being a system that is kind of a heavy hammer, something you only pull out for the biggest, hardest problems. And I think that that's unfortunate. I think actually the abstractions in this space that Kafka provides are better. And you want to use them not just for really big, high-scale applications, but also for little ones. There's plenty of small, important apps that could benefit from this. But it's actually hard to make the case that you ought to do that in a world where you have to undertake all the pain of operationalizing a big distributed system. But in the cloud, that's no longer the case. So we actually allow this to scale down. You can start and try it out for free, and you can run permanently for a few dollars a month at low scale for a small application, and that cost scales up as you get to larger scale. And so this can actually be a very effective ingredient now for even small applications. You can start with the right abstraction. And that scales all the way up to massive scale, the demo I showed before. And there's a ton of work in engineering that goes into getting good utilization, tuning the instances. You have to do this across all the clouds, of course, to really get the right performance out of the system and make the performance what you're selling. And I think this is one of the big changes in the cloud as well. I came from an era where computer programmers were trained to think about performance. They were trained to think about how many CPU instructions does it take to compute this or that. But nowadays, we don't really care about that. We actually care about cost. In many ways, cost is the new performance. We don't care about how many CPU instructions. We care about those instructions and how much they cost. And the ability to roll up all the right ingredients and target this for just the system that you're going to deliver, that's an incredibly specialized thing that no company really wants to take all the way to the end unless that's their core business. When you've done this well, it actually allows something really amazing. One of the things I always liked about open source was not just that you get the source code, but also that it was free. And so you could build these big systems without being as constrained by cost. And one of the things that's amazing about cloud services when they're done right is they can actually be cheaper than just free. If you take into account all the hardware and you take into account all the people that you actually need to build a self-managed system, it's actually quite expensive. Even if the software component doesn't cost you anything, you're still putting a lot into that operationalization. You're building the scripts that operate it. And then typically, with these big distributed systems, you're paying for a lot of underutilized capacity. And you have large teams of overworked people who are struggling to keep it up. And if this is done well, actually cloud systems can be net cheaper. And I think that's an amazing thing. The next capability that we launched was infinite storage. And this is one of the coolest. Storage in Kafka has always been something you have to think about. It's always there in the back of your mind. How much more space do we have on the local disks? Are we filling up such and such a partition? What will happen to performance if we end up with too much stored data and consumers come and read that? All of this kind of planning and pre-allocation that makes you have to predict what all your different applications are going to need to do. And we wanted all that to go away. And so in Confluent Cloud now, you can actually just write. And it will figure out all the storage needs and expand itself for you. And so this video is actually showing something I think pretty incredible. It's taking a cloud cluster, it's writing at large scale, and it just keeps going. And we wrote into this cluster for a little over a day. We wrote a petabyte of data before replication, and we just started with 0 bytes and wrote. And what did we have to do in the way of planning and operationalization and testing and so on to think about that? We didn't have to do anything. We just wrote it. That was it. And the storage was automatically taken care of for us. And I think this is incredibly powerful. It's one less thing that you have to worry about, and that's exactly what you need. The fourth capability is doing this everywhere. I think this is a hard requirement for modern cloud systems. The reality is the world is diverse. It exists in many places. And so we've built this stack in such a way that it can run really well in the three major clouds, in Amazon, in Google, in Azure. We've now made it available under the marketplaces of these accounts so that you can purchase it and draw down your committed spend with these cloud providers. And it feels very much like a native cloud ingredient. You can get it in whatever regions your applications are built. So if you're running in AWS US East, you can get Confluent Cloud in AWS US East and have it right there for you with private networking connectivity. And we try to make as much of this as we can available in the private cloud as well. So obviously, things like billing and marketplace don't necessarily apply there. But a lot of these core capabilities we're releasing. They run on top of Kubernetes. This is part of our Confluent platform offering. The 6.0 version of that comes with a lot more goodies. You should check it out if you're interested in that. So that was the first 4 months of Project Metamorphosis. There's still 4 more months to go. I think some of the coolest stuff is still coming. And since it's Kafka Summit, I wanted to provide a preview of what we're announcing, a set of capabilities around global operations. What this is going to make it possible to do is mirror data between Kafka clusters in any cloud And do that while preserving all the offsets and do it transparently with no additional operational capabilities. Just simple command sends your data between all these environments so that it's all perfectly in sync. Consumers can fail over transparently from one to the other. This is one more complicated thing that you no longer have to worry about. And I think that's a really good thing. So this has been our goal, to bring together Kafka and the world of cloud-native data systems. And I think this is an incredibly important initiative for Confluent, but I think actually for the Kafka community as well. Comes from what I shared about that journey at LinkedIn. I said that LinkedIn wanted to have the kind of data capabilities that Google had. We wanted to be able to really take advantage of our data, to harness it, to build applications around it, that was going to be an incredibly important and differentiating capability for us. And that was the charter of the data infrastructure team that I was a part of. But one of the realizations I had was, even as we were trying to provide this as a service, even as I told the team, think about what you deliver like an API. Think about our users as your customers. The reality was, if we were a service, we weren't a very good one. We were kind of like the phone company in the 70s, where you could get any data system you wanted as long as it was one of the 4 that we supported. And you could call our APIs, but calling our API often involved, filing a Jira and waiting for months or quarters until we could deliver the capacity for you. And the reality was our customer service wasn't great, right? And I think that this isn't that uncommon. I think very often this process of really trying to operationalize the broad use of data capabilities is really, really difficult. And the ability to do that as a first quality service is not quite there. And I think that that's changing enormously with the cloud. I think that we're really rewriting the boundary between what we build and what we buy right now. I think this is something that is a decision that's always existed in our industry. We don't build our own CPUs no matter what you're doing in your data center. That's because over time, where you want to spend your time and where you can differentiate changes. And I think that we're in the middle of one of those transitions right now. I think that although, for LinkedIn at that time in, 2009, 2010, it made sense to be building up these big teams internally to kind of operationalize open source systems or develop custom systems. I think that may no longer make sense. I think that the team that I built and ran at LinkedIn, I probably wouldn't be building now. I think that if you want to be like Google now, the way to do that isn't to build the way Google built. It isn't to build the way that LinkedIn built. It's actually to get these capabilities as a service. You can do that faster, you can do it better. And I think that's a very powerful thing. And I think this is important, not just for Confluent. It's not just about our service. I think this is actually important for Kafka itself. I think that ultimately, unless there are real cloud native offerings around open source projects like Kafka, I don't think that they're going to be successful in the modern world. I think, over time, if there wasn't such a thing for Kafka, I think Kinesis would be the thing that we built around, despite all the advantages an open platform has. And so I think it's incredibly important that these kind of things arise, and we're excited to be doing it at Confluent. I'm sure we won't be the only ones, but I think this is a really powerful thing. And it produces really good output in the software itself, really great contributions to the community. One of the ones that's going on right now is the work on KIP 500, the zookeeper removal. We thought this was a key thing for being able to scale elastically. We thought this was a key limiting factor. And there's a team right now that has a goal of having a zookeeper-free Kafka by the end of the year, which is not that far away, that can scale to millions of partitions on a single cluster. And I think that's going to be an amazing thing. I think it will make it even simpler to operate for those doing it themselves in their own data centers. It's going to make it a lot easier to run a managed service the way that we do. So I think there's huge synergy in the efforts here. And I think these kinds of investments, the ability to get this kind of stuff as a service, I think this is key. I think ultimately, if we want to build something which is part of the modern stack, if we want to make it really ubiquitous, we have to make it easy. I think time and again, what I've seen in our industry is the capabilities that are both powerful and easy. Those are the ones that succeed. It's not enough to be powerful on your own. You have to make something really easy to use. It has to be the simplest solution to the problem you have. And I think that if we do that, then we have this really exciting world ahead of us. I think that there's an opportunity for this to be a technology that really sits at the heart of the architecture of a modern company. that really ties together all the different systems, that's that locus where all of the streams of events of what's happening in a company comes together. I think that's an incredibly powerful thing to be a part of. I think it's something that we're all doing together. And I thank you all for your contributions to making that happen. And I hope that you enjoy the rest of day 2 of the conference. Thank you very much.
Coming up next, we have Sam Newman. Sam was set to join us as our keynote speaker in London, so I am personally delighted that we could invite him to join us for our virtual summit now. Sam's a well-known thinker in the microservices space. He spent 12 years at global consultancy ThoughtWorks and recently published the book Building Microservices, following his passion for the topic. Today, Sam is going to talk to us about how to reimagine the way we use data to make sure it works for us and we don't work for it.
Welcome to my talk, The Tyranny of Data. It sounds like a dark, depressing talk, and it's not supposed to be like that. It's going to be about the good things that you can do with your data, but first we're going to have to talk a little bit about all the bad things that data maybe causes us in our daily working lives. My name is Sam Newman. I'm sort of here because I'm one of the people known for being an expert in the area of microservices. I actually wrote a couple of books on the topic. So my first book, Building Microservices, was out several years ago, and I've just released a new book called Monolith to Microservices, which is all about how you take big existing systems and break them apart. And part of what you have to do when you break those systems apart is dealing with the data. And we'll come back to the aspects of databases and microservices a little bit later on. But to start off with, we should talk about data. Data is wonderful stuff. Data helps us get information about what our customers want and what they need. It gives us information about how we can help people. It's sort of the lifeblood of so much of what we do. And an awful lot of what our lives are as software professionals is working and managing and looking after data. Look, as a computer programmer, 75% of your professional life is going to be taking data out of a database and putting it on a screen. And if you're very lucky, the other 25% of your career is going to be taking data off that screen and putting it back into a database of some sort. Or is that right? Does our data always have to live in a database? The classic way we think of storing a database is the relational database. And the relational database is a wonderful thing. It gives us all kinds of powerful capabilities like transactions and, the ability to run ad hoc queries, and we can join across large volumes of data. But relational databases always kind of want to have all the data in it. We keep putting more and more data in it. It grows over time. And we start realizing that we have to take our application to the database to make it work. We start doing horrible things like putting database triggers and creating entire systems from stored procedures. The database grows because our data in it grows. And as a result, more of our time, energy, and attention is all around this big, giant, critical entity inside our application. Our databases, as they grow, become too big to fail for many of us. And the thing is, this is an issue, right? The database grows to such an extent that we're now scared of it. All of our critical information is in that one location. And as a result, any changes are really fraught. And so what do? We don't change the database structure. We find it difficult to look at different platforms. Any shift in making that data easier to work with are maybe sort of deprioritized because the risk associated with any changes are so great. And this is a real issue. Data is valuable. We want to lock it up. We want to keep it safe. So we put it in something which we hope is safe. We put it in the database. That's where it is. We hide it from the outside world, and woe betide us though if any of that information ever leaks outside. But again, let's think about that. Data is valuable. Does it make sense to put all of your most valuable stuff in one location? It's tantamount to saying, okay, we've got all of our valuables here and we put a big sign on it saying, steal me. Right? If anyone does breach that database and gets hold of your crown jewels, everything's gone. A large amount of those data breaches that we see are about one database being accessed. If all your most critical, most sensitive information is in one location, and that one location is breached, all of your data walks out the front door. And that is a real issue. Now, of course, we don't want this. We don't want the bad people out there to gain access to all of our information. And so when we put it in that one location, we do everything we can to protect it, but we can't escape the fact that every now and then we might make a mistake. We may leave a back door open that allows someone to gain access to our information. And if all of the data is in that one place, that magnifies the impact of one simple mistake that we might make. And this is quite aside from the fact that by having all of our data lumped together, we actually make obeying various different compliance out there much more difficult. Aspects related to complying to things like the GDPR or HIPAA compliance or PCI compliance. A lot of this is about how we treat and manage certain types of data. Now, if our most sensitive data is bundled in with our least sensitive data, and all of our application works off that one big giant data source, then effectively larger parts of our ecosystem fall under the remit of these various different schemes. When you're looking at PCI level 1 compliance, for example, sure, you might only sporadically store full credit card information, but if that's in with all the other data you store, any process that accesses that database, reading or writing, even if it never touches that particular piece of data, it's going to fall under the auspices of your quarterly audits. So a lot of the time it can make sense for us to try and break that data apart to reduce the scope of us having to comply to various different industry regulations. And this has all got a little bit more complicated recently. And we start thinking about data and where data lives. We've got this situation now where the EU courts have basically said that data for EU citizens can't now just be sent off to the US to work to be stored in the US. And that's going to cause a lot of tech companies to think differently about how they store data for different citizens. This idea, therefore, that we can store all of our data in one big place and sort of let everything be sucked towards it is kind of falling by the wayside a little bit. And this is a problem, right? Because relational databases work really well when everything is in them, but that causes us so many different difficulties. That big giant database that's been around in your enterprise organization for many years, where it sucked all that development energy and effort towards it. The data should be working for us, but all too frequently, we find that we are working for the data. And, I'd like to think that we can do better than that. Let's talk about microservices, because that's part of the reason I'm here, right? When we talk about microservices, one of the first things we focus on is this property of independent deployability. And this is the idea that I can make a change to a microservice and deploy that microservice into a production environment without actually having to deploy any of the other parts of my system. And this is the kind of the thing that we want from a microservice architecture. It would allow us to be much more effective and efficient in how we deliver our software. Now, if we zoom in and look at one microservice in isolation here, typically when we think about a microservice, we're thinking of all the code implements that microservice being packaged together as a single process. So the deployment unit of a microservice is going to be a process, maybe stuck inside a container. That process is going to communicate with other processes via some kind of network protocol. That could be something like a synchronous REST-based API, or maybe if we're being a bit fancier, some kind of nice topic-based system, maybe Kafka, for example. And when we start thinking about data, we talk about data being hidden inside a microservice boundary. Rather than using big shared databases, we say, well, look, the data that the shipping service needs is hidden away inside that shipping microservice boundary. And this sort of distinction of a microservice architecture is what causes us a lot of headaches, because that's moving us away from the big giant shared database, and that in turn causes challenges to us. Now, James Lewis, who was one of the an old colleague of mine, and that's actually one of the first people talking a lot about microservice architectures, he talks about microservice architectures as being an architecture which optimizes for autonomy. Organizations all around the world are moving to microservice architectures because they see it as a way to make their organizations work in a more autonomous fashion. Autonomy is always a bit of a questionable word. It can mean so many different things to so many different people. But when I talk about autonomy, I think when James talks about autonomy, primarily what we're talking about here is the ability to distribute responsibility. Rather than having to have all decisions made centrally, instead what we'd like to do is push decision-making responsibility into teams. Allow people to make decisions that are close enough to see the impact of those decisions. Allow people to react more quickly. Allow people to work more efficiently in parallel. Avoid the need to have to constantly coordinate between separate teams. And this should allow you to do more stuff. If you can add more developers who can work more in isolation, reducing the amount of coordination they need to make with other teams, they can get more things done and ship more products and make their users and make their customers happier as a result. And there may be other reasons why you might adopt a microservice architecture, but in my experience, this is the most common reason people pick microservices, because it allows larger development teams to still work efficiently without seeing the sort of huge downsides that can occur from just adding more people to the project. This is about getting the people we have working smarter. And if we get these boundaries right, and we embrace this idea of independent deployability, this sort of promise of organizational autonomy can come true. So independent working is a key idea here. Typically with the microservice architecture, we have this idea that a microservice is owned by a team. So team A owns the shipping microservice, team B owns the customer service and the account service, and team C owns the return service. So if I'm working in team B and we need to make a change in the functionality of the customer service, because there's property of independent deployability, I should be able to make that change and deploy that change into a production environment, release that functionality out to the users of that software without actually anybody else having to know, as long as the way in which that microservice communicates with the rest of the world remains consistent and the interfaces that it exposes remain consistent. Because here, the customer service is being used by the shipping service. So I want to make sure that when I make that change, I haven't broken the upstream consumer. Likewise, I don't want to break the interaction with downstream services either. So when we want to make independent deployability work, we need to kind of maintain backwards compatibility. And that's key to making independent deployability work. Now, maintaining backwards compatibility of something like a service boundary can be a bit tricky, but it's okay because we've got a cutting edge idea that can help us here. It's a cutting edge idea that comes all the way from 1971. And that is a concept called information hiding. Information hiding is a simple idea. It comes out of the work looking at how to define effective module boundaries, work done by David Parnass. And the idea is kind of straightforward. Let's consider a prototypical service. Here we've got a microservice of some sort, and I've got an outside party that wants to make use of the functionality that this microservice exposes or the data that it has. Now, we could decide to allow that upstream consumer to just reach into all the internals of this microservice, reaching directly into the database, directly accessing kind of internal objects and implementation details. The problem with this, of course, is when I'm working on that account service, it's very easy that as a developer, I might make a change to the internal implementation detail that ends up breaking compatibility with my upstream consumer. And if I don't have clear separation between what code and data can be changed freely and what code and data is actually part of that external contract, if those ideas in my head as a developer aren't separated, it's very easy for me to make changes that break external parties. And the big giant shared database is the ultimate shared implementation detail. If you allow other people to reach into your database, it becomes very difficult as someone who's maintaining that microservice to be clear about what things can change without affecting other people and what things might have a nasty ripple effect. With information hiding, what we're aiming to do is hide as much information as possible inside the boundary of a module, or in our case, a microservice. That's hiding implementation detail. In fact, the idea with information hiding is to hide as much stuff as you possibly can. You can always expose information or functionality later on that was hidden, but once you've exposed it, it then becomes part of the contracts that you expose with your external parties. So just be really careful about everything you share. If you're very clear and explicit about those interface points which are exposed and those implementation details which are hidden, your world becomes much simpler and much easier to deal with. As a developer working on this account service, I'm much more in a safe space now, knowing that if I change anything in that hidden world, I'm not going to affect anybody else. It's only the stuff in the shared world, the things that I've exposed to the outside party that I need to remain compatibility with. So this is why what we want is a well-defined service interface. When you have a microservice that exposes functionality over some interface, be it a REST-based API, a gRPC endpoint, or a Kafka topic where I'm emitting events, as long as I know clearly this is what I expose to the outside world, this is what must remain consistent. As a developer, I'm freed. I find it much easier now to work and make changes in an independent fashion. This is also good for the upstream consumers because they've got an explicit understanding about what it is that you provide them. So information hiding is super, super important. It allows us to make changes in a safe way. Information hiding fundamentally makes it much easier for us to implement backwards compatibility. And hiding data in this world is vital, and that's why we want independent deployability with our microservices. We need backwards compatibility. To make backwards compatibility a reality, we need information hiding. We need to hide our data to get that independent deployability. And this is a point that's often missed. So splitting apart data effectively can allow us to do more work in parallel, allow teams to develop products in parallel, get more stuff done with the people we've got. And it also gives us a lot more options about how we build systems and how we organize ourselves. Rather than having to bend our working practices to what the big giant shared database lets us do, if we can find ways to break that data apart, we open up a whole world of possibilities about how we solve these problems. So great, split data apart. It's all going to be fine, right? Well, there are some caveats here. There are some pain points that are caused by this whole approach. It's not just the issue of detangling your data, it's also the things we miss by not having that big giant database. But this, of course, is where companies all over the world are making use of Kafka. Kafka allows us, as we've probably all heard before, to kind of create this sort of central nervous system or backbone that runs throughout our organization. We can have processes that are emitting events onto this stream, consuming events from other locations. This becomes the way we communicate information across our system. And Kafka is going to do that for us in a consistent throughput mechanism. It's going to do that with a degree of ability to grow and scale. And it gives us a bit of sort of a shared place where this data can be shared and interchanged with applications written in different programming languages. And, hopefully we can all just get along. Isn't that a wonderful idea, right? That's the promise. But is that enough? Is just sending events around all we need to kind of solve this problem? When we think about the simplest way you might use something like Kafka with a microservice, we think about this in terms of, say, event-driven architecture. I'm making a change to a microservice, and as a result of some functionality that's been used inside that microservice, I emit some type of event. So in this case here, I've emitted an order updated event. Events are useful things to us. They are an indication that something happened at a given point in time, right? So there's a time at which this event happened. That can be useful for all sorts of purposes. We have information about the change that occurred. I then basically throw that event out, kind of metaphorically at this point, I don't even know where that event is going. I publish it on a topic, and it's up to whoever subscribes to that topic to do things with that information. And of course, as a microservice, I'm also free to consume events that are sent by other microservices. And so for sort of asynchronous event-driven communication, if that's as far as you go, Kafka is a fantastic tool for that. But it can also help us go further in terms of dealing with data, because it's not just a broker. Like, you could use Kafka like that, and it's great, but it's not really that different to some other types of sort of message brokers that you may have used. But Kafka has a whole lot of properties that really differentiates itself from other brokers that help us a lot when it comes to dealing with the tyranny of data. With traditional brokers, we typically think about the things that we send as being ephemeral. We fire an event, we send a message, whatever, and once that message has been consumed by the downstream party, it's gone. It's no longer there. With Kafka, of course, we can configure how long an event that we send over it lives for. This gives us the possibility of persisting that event forever, and that can be very useful. Think about that property of permanence can be useful because it allows new processes and applications to come on board to make use of events that were previously broadcast. I may have been emitting order updated events for days, weeks, months, years, and now maybe I want to roll out a new microservice that is going to recommend things to me based on my past purchases. Well, if my stream of events is already available and it's already been stored and made permanent within the kind of Kafka ecosystem, a new microservice that's spun up is able to ingest those messages, ingest those events, and start recommending things to me. Whereas if these events were more ephemeral in nature, I would have to get those events rebroadcast in order for that recommendation engine to start doing its job. So that property of permanence is a really key idea in terms of shifting our thought processes away from event-driven interactions being more of a transient, ephemeral in nature, and shifting us more towards the thought processes where events are now maybe a bit more permanent and therefore could solve some of the issues of how we get data and move that data around. Now, an event stream as an append-only set of records, this is, again, just with nothing else, is useful. There are lots of situations in which having an immutable append-only log is kind of fantastic. Think about financial ledgers, for example. Having this is what has happened, this is what happened at this point, this is exactly what was done. If you go no further, already for some processes and operations that you might need to implement, Kafka's given you a whole lot of stuff out of the box. We can go further though, right? But let's pause for a moment. Isn't sharing events just like sharing a database? If I'm saying sharing events and I'm allowing lots of processes to combine and access those events, isn't that the same thing as just saying everybody talk to my database? Well, it's different in a couple of ways. Firstly, with an event, you've made a conscious decision to emit it. You said, this is something that I'm happy to expose to the outside world, and hopefully some conscious thought has gone into that. When we allow people, on the other hand, to just access a database directly, we don't really think too much about it. We just say, access the database. And once they access that database, they access the whole database, right? Every table, every relationship is being accessed potentially by an external consumer. When I emit an event, on the other hand, it's just that one event that I'm having to reason about. It's much smaller in scope, and therefore it's much easier to maintain compatibility of that event. But fundamentally, the fact that you've decided to send that event out to the wider world, that conscious decision to send it out, makes it part of your external interface in the same way a REST API would. And so this is significantly better than just sharing a big giant database from that point of view. But there are other problems. If we're sort of having data broken apart, we're sharing these events, there are other things that we get from a relational database that we've kind of lost. What about joining data across large sets of data or ad hoc queries? I might want to do like a bit of ad hoc reporting and say, I can't do this if I'm firing events from microservices. And again, of course, we can solve this problem with Kafka. If you've got your stream of events being thrown across your enterprise or, this lovely river of information to which you can dip in and grab whatever event you might need, well, there's no reason why you can't just funnel that to a big old database. I think the issue is, and people say, well, isn't this back to what we had before, a big giant database? The issue here is that we often have built an application around a database, and that database grows and grows and grows, and it becomes all things to all people. If what we want is a database dedicated for reporting, for doing things like ad hoc querying, we can design the schema, we can pick the technology that's fit for that purpose, picking the right tool for the job. We can then use Kafka to bring all of that information from us from all different systems and funnel it into the location we need. This pattern's kind of called the reporting database. The idea here is that rather than sort of tying your reporting workflows to reading data from inside an application, instead you have a dedicated location where that data is made available to you. And this is a really useful model. We're decoupling how an application might store data for sort of online transactional processing reasons. And instead we're saying, no, this is the world where you do your ad hoc queries and you do your joins. You pick the right technology, you can attach Tableau or Click or whatever else it is to those systems. And the workflows really for people saying data warehousing and analytics don't necessarily need to change. We've made an architectural change by breaking our data apart, by breaking our workloads apart, but Kafka can still ensure we can carry on operating with workflows that are familiar to us. Kafka and associated tools help. Now, of course, we can do things like I'm just going to fire an event and then have something that reads that event and writes it into a database. And sure, I could do that. But, we could go a bit further. I'm sure, some of you have heard of Debezium. Debezium is fantastic. I don't know if I'm pronouncing it correctly, but that's how I say it. Debezium is a really useful open source tool that makes this whole process much easier. What Debezium can do is it works like a change data capture tool. So change data capture processes work by looking at changes made in a database, specifically look at the commit log. Whenever you make a change in state in a database, it's actually appended to a commit log. Tools like Debezium look at that commit log. When a new entry appears, they trigger some behavior. Debezium runs as a Kafka connector. What it does is when you write into your database, you can configure which parts of that database it cares about. You can pick up that data and send it somewhere else. So this becomes a very good way of getting data out of your microservices and putting it into, say, an analytical system. This can also be incredibly useful if what you're trying to do is actually pull data in from maybe other legacy systems that can't be changed as easily. And there's no surprise that Debezium is so widely used for this purpose because it is fantastic at that. So we've broken data apart. Debezium and Kafka together can help us bring that back together again. So that's cool, but that feels like we're still kind of just recreating, at least from a reporting point of view, a bit of an old-fashioned world. And there's nothing wrong with that. there's some fantastic things that we can do with kind of reporting databases and data warehousing. But, we were promised jetpacks. So is there something else that we can do in this situation? And this, to me, is what's got me really excited over the last few years. It's been seeing the development of KSQL, now what we call KSQL DB. So KSQL DB allows us to kind of create SQL-like statements that allow us to do sort of stream processing either in Kafka clients or in a dedicated KSQL DB server. So what I can do is say, okay, I've got my order service. I'm emitting these events, these order updated events, right? So I'm going to say the orders are being placed. And so I could create a push query that basically is like a constantly updating query. So I can define that query using a SQL-like syntax. I can then effectively have that dynamically updating so I can subscribe to the results of that query. And as these new events appear on that stream, this is going to automatically update and give me a running total, telling me how much money we've made today. And that's kind of fantastic, right? So rather than having to write a dedicated program that reads a stream and updates a count and then emits a count, I can just take a query, run it on KSQL DB, subscribe to the results. Really, really simple. It's a great idea. We can go further, of course. And this where things start getting interesting is when you start crossing the streams, right? Rather than running a query on just one topic, right? What happens if I want to start pulling information together from multiple different locations? Maybe what I want to do is say, well, I've got all these orders coming in, but I want to see how much money we're making on a genre by genre basis. We're selling pop CDs, rock CDs, Hoover Core CDs. What segment of our market are we making the most money in? Now, the order placed events don't contain the information we need. They just say, this is how much this order cost. We need information from another source. And the catalog service is where all the information about the albums that we sell, the CDs that we sell, we're a cutting edge organization over here in the UK, all of that information is coming in those events. So we can define a push query that pulls in information from the genre associated with a compact disc. And when that gets sold, we're able to associate the sale to the right genre. So we can now have a lovely updating table showing us that rock's doing okay, hip hop's doing even better, but our biggest seller is obviously, as it always should be, Death Polka. We sold over $2,500 worth of Death Polka today, which I think is a good day's business. So these push queries are fantastic. They're like kind of SQL statements and selects on steroids because they are dynamic. They continually update. And for sort of asynchronous workflows, they're really great. And they sort of, if you're already in that asynchronous event-driven world, they fit that mindset so well. But of course, we often have different kinds of interactions we want. We want to be able to ask just ad hoc questions like, what's the state of a given thing? How many orders has Sam placed today? Or what was Sam's most recent order? And before, that was a bit difficult when all we had were these sort of push queries, but now we've also got pull queries. So I can ask questions like, what was the most recent order by Sam? And this is moving me more to a world where it just looks like a traditional select statement to an extent. From the point of view of the application making that request, it's like I'm talking to a database. It doesn't feel fancy in a way. So we've kind of started to make Kafka be real time. It can bring data together from different places. I've got these amazing sort of streaming updating queries. But if all I want is to use it kind of like a normal relational database, guess what? I can kind of do that too. So this for me is what's so exciting about the tooling in this space, right? We're moving from a world where we had to work for our data. And now we're kind of moving to a world where we've recognized that if we can break that data apart, it gives us all these great benefits in terms of independent working, but all these challenges too. And some of the stuff in this ecosystem and some of the advances that have been happening in KSQL and KSQL DB, they just make me feel like, okay, we've actually kind of come up with some solutions to that whole problem. We can have our cake and eat it. The data is now working for us more than us working for the data. So I'm not going to lie to you and say that this is going to necessarily be an easy journey. I think going from a standing start to we're all in on KSQL DB, that's a lot to bite off. But I think you can see a sort of a gradual progression of ideas here. Just using something like Kafka initially to just move data around, putting data into your data warehouse, for example, getting yourself familiar with that ecosystem, then you start doing a little bit of push query stuff here and there. And then eventually you might find that you can push all of that work into the KSQL DB ecosystem. So there's a lot of ideas here and thinking about, well, how do I get my head around this? where there are the resources that I can look at to get to think about these ideas. Shifting from database thinking to thinking in terms of events. A great resource here would be this book, Designing Event-Driven Systems by Ben Stopford. It's a very short read. Ben, of course, has been at Confluent for a very long time, and this book is freely available, and it's a really, really good read. I have to say that because I wrote the foreword. The nice thing about the book is that Ben sort of takes you through these ideas a bit at a time. And just like with kind of the Kafka, you can just use Kafka for the sort of simpler pieces first, and these ideas grow with you. And Ben takes you on that journey. So it's a great, great read, and I do recommend reading it. As I say, it's not a long read either. It's really a nice, concise overview of some of these ideas. The other thing that can be really challenging in this ecosystem is the process of breaking your database apart in the first place. I cover that in a lot of detail in my book, Monitor Microservices, specifically chapter 4. I talk about all horrible things like what happens when you have to break a join relationship and these sorts of things. If you want to know more information about the work that I do training, advisory and consultancy services for companies all over the world. You can find information at my website. You can also find information there about what's happening with the second edition of Building Microservices, which is a work in progress. I'm hoping it's going to be released towards the middle of next year. I really hope you've enjoyed the summit so far, and I hope you enjoy the rest of the time here as well. And thanks so much for watching.
Jay and Sam, hey, thank you for those keynote contributions to Kafka Summit. I really appreciate them, and I know the audience does too. Now, we are done with keynotes, which means it's time for sessions. So buckle your seatbelts. You're going to have a bunch of learning to do over the next few hours. Also, one other thing I wanted to mention in the conference platform, there's a poll where you have an opportunity to pick one word, just one word to describe Kafka, or your experience with Kafka Summit, your experience with the Kafka community. You have some flexibility here. I'm constraining you that you can only give one word, so I want to broaden the domain, but it's something about your work with Kafka. One word. Go take that poll in the conference platform. Afterward, we'll create a word cloud that summarizes all your thoughts on Summit and Kafka and the community, and I am really looking forward to what that says. So, think of that word, go do those sessions. See you soon.